Oh, sorry. Never ceases to amaze me the way Keynote always takes a half hour to load whenever I'm running late. Anyway, if you did read the email last night, Homework 5 is now posted on Sakai. Exam, as I announced on Monday, what I'm leaning towards at this point is we're just going to do a hybrid thing. It'll be a regular take-home final like there is on the syllabus, but people will have the option, if you want to write like an NIH R03/R21 proposal, you can do that as part of your final, and then you can just answer one question on the final of your choice rather than doing the entire final exam. My thinking was there are some PhD students in this lab who might want to run their own lab someday, and knowing how to write an NIH grant is a very important skill, and trying to make this class relevant, but it may be not as relevant for undergraduates and master's students, so I didn't want to torture anyone with it if it's not a skill that you're ever going to use. So if people have concerns about that, let me know. Otherwise, that's the direction I'm headed, and I haven't really figured out how I'm grading it yet, other than to say that, like, if you write the grant and do a really good job, you've probably guaranteed yourself an H. And if it's just kind of a so-so or poor job, well, then it'll depend on the rest of the class. So trying to make it so it won't hurt you if you go that route, because it will probably require more work than just doing the final. But yeah, in general, I would say choose what you do based on what you hope to learn from this class, not what you want to do to maximize your grade, because maybe I shouldn't admit this, but I'm usually a pretty easy grader, so I wouldn't say, oh, I'm going to do the grant even though it's not going to help me just because I want a better grade in the class, because yeah, anyway. So today we're going to discuss penalized regression in more detail. I briefly introduced it on Monday, but today I'll describe how to actually implement this in R and so forth. From my point of view, these penalized regression methods that I'm teaching today are some of the most useful tools in modern statistics, and they're not that hard to do when all's said and done. I mean, there's a bit of a learning curve, but it's not terrible. And I would really love to see these methods get used more and stepwise regression get used less. So that's why I'm teaching it in this class, in hopes that it'll be one small step towards this. Well, anyway, recall from Monday and the last couple weeks in general that when you're trying to do a regression, you have several predictors that are correlated with one another. That will increase the variance of your model. And if you get enough predictors in your model, the problem is unavoidable. If you're trying to predict an outcome based on a microarray data set with 30,000 genes or something like that, there's multicollinearity and there's nothing you can do about it. Even if you just have like 5 or 6 predictors, it's most likely going to be a problem. And if you just mindlessly apply ordinary linear regression, you can get incorrect answers. Or if the number of predictors is greater than the number of observations, there won't even be a unique regression solution in the first place, so you need to figure out ways to deal with this. So, one approach that personally I'm a big fan of, that I don't think it's used enough in the statistical world, is penalized regression, which, as we briefly discussed on Monday, it favors solutions with small coefficients, the idea being that a regression solution with small coefficients is less likely to be overfit than a solution with larger coefficients. There's various flavors of penalized regression. This is a very active research area right now. I'm just going to describe 2 of the most commonly used methods, because I could spend weeks talking about this, and this is already a little advanced for an intro course, but the basic idea is, in ridge regression, you try to minimize, rather than just the sum of the squared errors and ordinary least squares, you only minimize this piece, the difference between the true value of y and the predicted value of y. For ridge regression, you try to minimize this quantity plus tuning parameter times the sum of the squared coefficients. The idea, if these squared coefficients are too large, then the model will favor us. Then this criteria will favor a solution with a slightly larger sum of squared errors if it's associated with a smaller set of coefficients. LASSO is similar, except that rather than the penalty term being the sum of the coefficients squared, it's just the sum of the absolute value of the coefficients. That has certain advantages over ridge regression, as I'll discuss here in a minute. So just an illustration of a situation when penalized regression might be useful is a famous data set called the Boston housing data. I put a copy of this data set on Sakai if anyone wants to try any of the examples today. But in this particular data set, they were trying to determine what variables affect the price of housing in various neighborhoods in Boston. So they went through 506 neighborhoods in Boston, collected 13 possible predictors of housing prices. The goal of this particular experiment is to try to predict the median value of homes based on these 13 different predictors. So here's a pairwise scatter plot of the Boston housing data, and even on my screen I can't really read the names of the variables. But you look at this and there's some pretty clear evidence of multicollinearity. See, like right there, pretty obvious that as one variable increases, another increase. There's a pretty strong one down in that corner. In general, it's pretty obvious that we're not seeing just random scatter here, that a lot of these variables are correlated with one another. That suggests that multicollinearity is going to be an issue, and that if we use some type of penalized regression, we might do better than if we just mindlessly apply ordinary least squares. So, how do we know if penalized regression is actually going to help? The idea is, as I said, penalized regression has lower variance than ordinary linear regression. We hope that will result in more accurate predictors. We want to see if that's actually true in practice. And that turns out, in determining if penalized regression actually helps, is trickier to do than it seems. That how do you know if penalized regression will give you more accurate predictions than ordinary least squares? Well, one approach that you might try is like, well, we'll fit an ordinary least squares model to the data, we'll fit LASSO to the data, we'll fit ridge regression to the data, and we'll see which model gives the smallest error. Well, unfortunately, that doesn't work because by definition, ordinary least squares minimizes the sum of squared errors. So if you just look at the sum of squared errors on the data used to fit the model, ordinary least squares is going to win every single time because by definition, no other model can do better by that criteria. And that also doesn't address the issue of overfitting, that if a model is overfit, then you'll get very low error on the data set used to build the model. You'll get a very poor error rate if you apply it on a new data set. So if we just used the brain dead criteria that I just described, the model could be overfit and it would favor ordinary least squares and would never know that. So if you want to see if these penalized methods actually do better than ordinary least squares, a better approach is to do what's on the following slide. That basically just split your data in half. One half you call the training set, one half you call the test set. This works best if your data set's large, but you can use it for pretty much any data set you want. So you split your data in half, and then you take one half of your data and you fit your model to that half of the data. And once you have this model in hand, you apply it to the second half of your data, the test set, which your model has never seen before, and then you predict the values of y on this test set, and you look at the sum of squared errors on this test set rather than on the training set, and that gets around the overfitting problem, that if your model's overfit, you'll get really small errors on your training set, but much larger errors on your test set. Whereas if you have a good model, it should produce reasonably small errors on both. Well, the hope would be if penalized regression is really improving on ordinary least squares, then you would expect that the error rate on the test set will be smaller for these penalized methods than it is for ordinary least squares. So we try this on the Boston housing data. I just randomly split the Boston housing data into a training set and a test set with 253 observations each. There's a total of 506 observations in this data set. And so I fit a ridge regression model and the LASSO model to the training set for various values of lambda. Recall that if both penalized regression methods, if I let lambda equal 0, then it's the same thing as ordinary least squares. So if I analyze these two penalized regression methods like this, I'm also analyzing ordinary least squares by default. I used these various models to predict the median price of housing on the test set and calculated the sum of squared errors for each possible value of lambda. And what did this look like when I did it? First of all, I tried ridge regression with lambda equals 0 and then just increased lambda and looked at the sum of squared errors on the test set. And this particular data set, I mean, if for lambda equals 0 at the ordinary least squares case, we get a sum of squared errors of about 5403. You'll notice as lambda increases, we start doing ever so slightly better. I mean, it isn't a huge improvement in this particular case, but it does improve somewhat. We see that the sum of squared errors on the test set is minimized for about lambda equals 9. Then it starts to increase a bit. So we're not getting drastic improvement here like we sometimes see, but we are seeing some type of improvement suggesting that the ordinary least squares model may be overfitting slightly or may be suffering from multicollinearity issues. And if we penalize the coefficients to force the coefficients to be smaller, we get a model that's slightly more generalizable. And LASSO, on the other hand, for this particular data set, doesn't seem to improve the predictive accuracy much. For various values of lambda, in each case we do slightly worse than we did in the case of ordinary least squares. Although, as I'll discuss here in a minute, that's not necessarily the end of the world in this particular context, because LASSO does variable selection. If you want to reduce the number of variables in your model, LASSO will let you reduce the number of variables without losing too much predictive accuracy. And honestly, this example is somewhat unusual. More often than not, when you do LASSO, as you penalize the model, the predictive accuracy of your model will actually increase. This is just kind of an unusual data set. So it looks like ridge regression, for most values of lambda, it will improve the predictor value of your model at least somewhat. LASSO doesn't do much for your predictive accuracy, but if your goal was to reduce the number of variables in the model, it can still help with that. This raises the question, how do you choose the value of lambda in general? That both ridge regression and LASSO require you to choose lambda, and it's hard to know in advance which value of lambda will give you the best predictions. You could do the training set, test set thing that I just described, but that requires you to basically throw out half your data when you fit the model, which is something that you typically don't want to do, particularly if your sample size is small. So there's another way to estimate lambda using a procedure called cross-validation that's usually considered to be preferable. And here's an outline of how cross-validation works. Rather than splitting your data in half, you split it into about 10 partitions, and then you cycle through the partitions one by one. So say you start with partition 1, then you exclude partition 1 from your model, fit the model using partitions 2 through 10, and develop a model on that for various different values of lambda. Then for each different value of lambda, try to predict the values of y in partition 1 for these various different values of lambda. Then repeat the process for partition 2. That leave partition 2 out, fit the model using partition 1 plus partitions 3 through 10, get a model for various different values of lambda, then predict the value of y on partition 2 for all these different values of lambda. Cycle through this procedure for all 10 partitions and various different values of lambda, and for each value of lambda calculate the sum of squared errors for the predictions on the left out partitions for all the different values of lambda. The value of lambda that gives you the smallest cross-validation error rate is the optimal value of lambda. And rule of thumb is that you usually want to choose a lambda that's slightly larger than the value of lambda that gives the minimum cross-validation error rate. The idea is that it's usually better to underfit the model slightly than overfit the model slightly, and the model with more large coefficients is more likely to be overfit. So it's conventional to find the value of lambda that minimizes the sum of squared error, the cross-validation sum of squared errors, and then go one standard error beyond that. Plus, just playing around on simulated data sets where we know the correct answer, it seems that if you go one standard error beyond the minimum value of lambda more often than not, that gives you closer to the quote-unquote true answer than if you take the minimum. I don't really understand why, but that seems to be the case. And usually when you do cross-validation, I'm definitely not going to ask you to code this in R. It's a headache to code that I have trouble coding myself, to be quite honest. But there's some software built into R that will do this for you, and when you've done this, then you can try to visualize the result by just plotting the cross-validation error rate versus lambda. I coded this by hand for the Boston housing data, where I just randomly split the data into 10 partitions, fit the model using 90% of the data, predicted the values of y for the 10% that I left out, and repeated this 10 times. I remember when I created this slide a couple of years ago, it took me like 2 hours to get the code to work correctly. I sure as heck am not going to ask you to do this in this class, and as I'll show you in a minute, since I took the time to create this slide, there has been software written that will do this for you, but it illustrates the idea that, consistent with what we saw on the earlier slide, that for lambda equals 0, the ordinary least squares error rate. As lambda increases, the error rate tends to go down slightly. It seems to give minimum cross-validation prediction error at lambda of around 4 or so, at which point the error rate starts to increase again. As I noted earlier, you may want to go a little bit past the value of lambda that minimizes it, maybe go up to about 6, 7, 8, something like that. I didn't calculate standard errors for this particular plot, but in general you might want to go a little bit past it. we saw on the other slide that it's lambda of about 8 or 9 that gave us the minimum test error, suggesting that this value of lambda may be not quite conservative enough. So, you can, as I said, programming R to do cross-validation is a big headache. I sure as heck am not going to ask you to do it in this class. And there's existing R packages that you can use to do cross-validation for both ridge regression and LASSO. And there are other ways to find the optimal tuning parameter for ridge regression that I'll describe in a minute that also tend to work pretty well. And one problem with teaching penalized regression in an intro course at this point is, I mean, just in the 3 or 4 years that I've taught this class, software to fit these models was almost non-existent when I first taught this class. Now, people have released some R packages to do this, so software at least exists. The problem is, given that the software has just barely been released, I mean, like LASSO in particular, I mean, the LASSO method wasn't even proposed until about 1995, and it was only about 2004, 2005 that people developed an algorithm for fitting a LASSO model that was reasonably fast. It's only in the past 4 or 5 years that code to fit a LASSO model has been available in R and other statistical packages. That's a big part of the reason why this methodology doesn't get used very much and that you still see stepwise regression. It's just, it's new methodology, so I think the reason people don't use it is because they don't know about it. But after that little digression, since this is new methodology and new software, it's not very polished at this point. And the syntax is kind of clumsy, and R wants you to input your commands in a very specific form and will give you errors if you don't. So, I mean, in the past, people have been able to do the homework successfully based on my lecture notes. And if you can figure this out on your own, more power to you. But if you need to use this for a paper or whatever, it might be worthwhile talking to a statistical expert, just because some of these commands are kind of a headache to use. Oh, first I'll describe ridge regression in R, and last night I debated about the best way to teach ridge regression in R, because there's another way to do this that I'll describe briefly at the end of today's lecture that in general I think is better than this lm.ridge function that I'm about to teach you. The problem with the other way of doing ridge regression in R is it has a critical bug that hasn't been fixed, and I will show you a workaround for that bug later today. But it involves one of the most confusing and convoluted R commands I've ever seen. Plus, it would have required me to completely rewrite all my lecture notes, and I wasn't sure I wanted to do that at 2 a.m. last night. But if you look at this lm.ridge stuff and think this is a major headache, I don't want to do this, there's another way to do this that I'll show you in a couple minutes. But there'll be 2 ways to do ridge regression in R, and they're both clumsy and awkward, and you can just choose whichever one you hate the least is the bottom line. Oh, anyway, as of several years ago when I wrote these lecture notes, the only way to do this in R was to use a function called lm.ridge, which is in a package in R called mass. Capital MASS. This package is already installed, so you won't have to do install.packages, but you do have to load it using library mass before you run the command. So I read in the Boston housing data, and to fit the ridge regression model, I say housing.ridge equals lm.ridge. It's the same syntax for an LM model, I go lm.ridge med v, that's the median value of a home, twiddle dot, saying predict the value of median home value based on all the 13 other predictors in the data frame using the housing data frame, and I just arbitrarily say lambda equals 5 in this case. So in general, if you say lm.ridge y twiddle x or y twiddle x1 plus x2, whatever the case may be, it'll do ridge regression with a value of lambda equal to whatever parameter you specify. You need to load the mass library before you can do this, and you can specify more than one value of lambda simultaneously, as I'll show you here in a second, because usually you'll want to try a bunch of different values of lambda and see which one gives the best results. So how do you choose lambda? Well, there's a command called select, and select, just to confuse you further, as I just described cross-validation to choose the tuning parameters. Select does not use cross-validation. It uses a couple other estimators that people have cooked up that are supposed to be good approximations to cross-validation. In particular, this GCV statistic is called Generalized Cross-Validation, that tries to approximate the optimal value of lambda for cross-validation without actually doing cross-validation. Yeah, it's all highly strange. But in general, if you want to try to estimate the best value of lambda, you fit an lm.ridge model. And here note that I'm fitting a model with a bunch of different values of lambda. I say sequence from 0 to 15, length equals 1,000. That tells R to try 1,000 different values of lambda, starting at 0, going up to 15, just evenly slicing up the interval between 0 and 15. And then the select command tests every single one of these possible values of lambda. According to these 3 different criteria, it gives you the optimal value of lambda. And most of the time they'll give you similar lambdas consistent with what you see here. When in doubt, GCV seems to work the best, but yeah. And later on in today's lecture, I'll show you how to use a different R package that can do traditional cross-validation for ridge regression so that you don't have to mess with this whole select command. It's just, that's the function that has the bug in it, so that's the reason I didn't want to make it the center of today's lecture. But in general, if you say select ridge object, it'll give you an estimate of the optimal value of lambda, and you'll want to specify a whole range of lambdas rather than a single lambda if you want to pass the results to select. If you only try one value of lambda and pass it to select, well, it'll tell you to use the lambda that you tried because it was the only one that you tried. The select command intends you to try a bunch of different values of lambda, and it tells you which one is the best. And fitting this model to a bunch of different values of lambda is actually very fast in R. If even doing it for 1,000 different values of lambda is basically an eye blink, so this shouldn't take too long to do, unless you try a bazillion values of lambda and your data set is huge. And one annoying thing about the lm.ridge function is for some reason there's no predict command for it. I don't know why. To me, that's a really dumb oversight. But if you want to make predictions using lm.ridge, you have to just extract the coefficients using the coef command, like we discussed for an ordinary least squares regression model. Then to actually make the predictions, you have to do matrix multiplication, take your 13 predictor variables, convert it to a matrix. In R, this command %* tells R to do matrix multiplication. Hopefully you've seen this before if you've taken linear algebra. If you haven't, you can just take my word for it that it works. and basically it ends up just multiplying the variables in the first column by the first coefficient, the variables in the second column times the second coefficient, then adding them up, and then you finally add the first coefficient, which is the intercept. So, like I said, it's clunky. If you didn't understand this command perfectly, don't worry about it. You can just basically copy my code here if you need to make predictions using lm.ridge on the homework or whatever. And once again, later in the lecture, I'll describe another way to do this that's slightly less clunky. And in general, if you say coef of a ridge object, that will give you the regression coefficients. Just like if you say coef of an LM object, it will give you the coefficients of an ordinary least squares model. This %* command performs matrix multiplication. If you've never seen that before, don't worry about it. You can just copy the code I did. And this as.matrix command that I guess I forgot to explain on the previous slide, this is another one of those annoying R things that if you do read.csv in R, by default it will store it in a data structure called a data frame in R. And for the most part, a data frame and a matrix are more or less interchangeable. The big difference is a data frame, some of the columns can be categorical, whereas a matrix, everything has to be numeric. And you would think the R would be smart enough that if you have a data frame consisting of nothing but numeric values, that if you tell it to do matrix multiplication, that it would do it. Unfortunately, R is not that smart. If you just say housing of 1 to 13% coefficient, it will give you an error saying that you can't do matrix multiplication with the data frame. So you have to do as.matrix to tell R to convert it to a matrix rather than a data frame so that you don't get the error. Like I say, clunky, but it's the best we can do. And if you want to do LASSO in R, this R package is a little bit more polished than lm.ridge. It uses the glmnet function in R. This package is not built into R. You'll need to install it using install.packages before you try it for the first time. And to use the glmnet function in R, you just say like housing.glmnet equals glmnet. Then it takes two parameters by default. The first parameter is a matrix of x values where each column is one of the predictors. The second parameter is the y variable. So in this case, it says predict column 14 of the housing data frame. Column 14 is the median home values column based on the first 13 predictors. The one thing that's clunky about this particular function is that once again this x variable has to be a matrix. If you give it a data frame, it'll blow up. So you have to do as.matrix to convert it to a matrix before you run the command. And if you do this, it will automatically fit a LASSO model to a bunch of different values of lambda. And I think most of this I said already. In general, glmnet xy will fit a LASSO model to predict y based on x. If x is a data frame, you need to do as.matrix to convert the data frame to a matrix. And glmnet will automatically try a bunch of different values of lambda, so you don't need to specify that automatically, and you need to do install.packages glmnet to install the software before you use it for the first time. And cross-validation can be done very easily using the glmnet package. The command is called cv.glmnet or cross-validation glmnet, which takes exactly the same syntax as the glmnet command. This just, rather than fitting the model, it does cross-validation. And then if you want to see the plot of the cross-validation error rate for different values of lambda, you just plot the CV object you just created. So if you do this with the Boston housing data, you get a plot that looks like this, and it suggests that you can improve your predictions very slightly for small values of lambda. It looks like the reason that my out-of-sample error rate wasn't decreasing when I tested this earlier is that I wasn't trying lambdas small enough. Here, the first dotted line is the value of lambda that gives you the minimum cross-validation error rate. The second dotted line is one standard error above it. So it looks like the optimal model, you might be able to exclude one or two of the predictors. These numbers at the top tell you how many non-zero coefficients are in the model. Recall, LASSO forces some of the coefficients to go to zero. So it looks like with about 11 predictors, rather than 13, you minimize your cross-validation error rate. With about 8 or 9 predictors, if you go one standard error above it, suggesting that if you penalize the model to reduce the number of coefficients in the model, you do slightly better than if you just fit a regression to the full data set, although in this case the improvement is not huge. And in general, if you go cv.glmnet x, y, it will try to find the optimal value of lambda to predict y based on x using cross-validation, and you can pass the output of this function to the plot command to draw the graph of the cross-validation error rate versus lambda. And if you want to make predictions, that's thankfully less clunky in glmnet than it is with lm.ridge. It's still a little bit clunky, but less so. There is a predict command for glmnet that works okay. If I say predict, recall that I saved the LASSO model as housing.glmnet, then I say new x as.matrix housing 1:13. This just gives me the predictions on the x's that I used to build the model. If I had left out part of the data as a training set, I could say new x and then give it my training set. And then you have to specify a value of lambda to do this. You'll note here I say housing.glmnet.cv and then I say lambda.1se. What that tells R to do is just take the value of lambda that's one standard error above the value of lambda that gives you the minimum cross-validation error rate. So in other words, rather than having to squint at this plot and say, lambda looks like it's about e to the minus 1.2 or whatever the case may be, I can just say housing.glmnet.cv $lambda.1se, it will give me that lambda automatically. And if I wanted the minimum value of lambda rather than the value that's one standard error above the minimum, then I could say $lambda.min rather than lambda.1se. In practice, I recommend that you use lambda.1se because that tends to give better results. And if you want the coefficients rather than the predicted values, there's a coef command. Just once again say coef housing.glmnet. You need to specify the value of lambda. Say s equals housing.glmnet.cv $lambda.1se again. See, for this particular model, it's forced 4 of the regression coefficients, actually 5, to go to 0 because it decided that the age parameter is redundant, so we managed to throw out 5 of the 13 variables with a minimum decrease in predictive accuracy. For many problems, you'll actually improve your predictive accuracy when you do this, so this is why I pretty much always prefer LASSO to stepwise regression. The LASSO accomplishes exactly the same thing as stepwise, that is reducing the number of predictors in the model, but you can do it in such a way to guarantee that you're not overfitting, whereas stepwise regression tends to overfit. And in general, if you say predict on a glmnet object, new x equals x, s equals lambda, that will predict the value of y for a given value of lambda based on a lasso model. If you say coef and specify lambda, that will give you the coefficients for a certain lambda. And if you have the output for cv.glmnet, if you can go cv glmnet object $lambda.min, that will give you the lambda that minimizes the cross-validation error rate. And if you go $lambda.1se, that'll give you the lambda that is one standard error above the minimum value of lambda. And as I alluded to earlier, if you don't like the lm.ridge command, and frankly I don't, in the past year or two, they've updated the glmnet command so that the glmnet command will also fit ridge regression models in addition to lasso models. The one problem is there's still a bug in the glmnet package for fitting ridge regression models that has not been fixed. And I will show you a workaround for that particular bug, but it involves possibly the most horrible piece of R code that you'll see in this class that I will not even attempt to explain to you what it means. But if you want to use this, you can just copy what I put on a couple slides and it'll work for you. So, how do you fit a ridge regression model using glmnet? It's the same thing as glmnet for lasso. You just have to add this additional parameter where you say alpha equals 0. That will tell you, I won't explain what this parameter alpha means, but the short summary is that tells you that to fit a ridge regression model rather than a lasso model, if you don't specify to alpha, it defaults to 1, which gives you a lasso model. So we try to fit a ridge regression model using glmnet. So far, so good. Then we try to use cv.glmnet to perform cross-validation, same syntax as before, as.matrix, housing 1 to 13, housing 14, alpha equals 0. So far, so good. The problem arises when we try to plot the cross-validation curve. If you just do the plot housing.glmnet.ridge.cv, you will get this error right there due to a bug in the glmnet package. Now, that may not even be that big of a deal. I mean, you don't even really need to plot the CV curve. You can just use $lambda.min, lambda.1se, and those values are correct. But cross-validation error curve is pretty. It's cool to include in papers and stuff. It's highly annoying that that function doesn't work. So if you want to get it to work, you can do the following workaround, which, as I said, this may be the most horrific R code in this entire class, but the command you need to do is on this slide right here that I'm not even going to attempt to explain what the heck this means. But basically, take this code here, copy it exactly as you see here, only change the name of housing.glm.ridge.cv to whatever you named your ridge regression object. If you copy this code exactly as you see here and run it and then try to plot it, it will work. I spent like 45 minutes last night trying to figure this out, but I've tested it enough times that workaround does work. And if you're a real masochist, I can explain why it works, but you don't want to know. Trust me, you don't. And the advantage to using glmnet rather than lm.ridge is that you can get predictions for your ridge regression model much more easily. You don't have to use all the silly matrix multiplication stuff. You can just use the predict command and the coef command, and you also don't have to specify your own values of lambda and use select to try to find the optimal value of lambda and wait forever for select to run. you can just use cv.glmnet. It will figure all that out for you. So, like I said, last night I gave some really serious thought to just scrapping all the material on lm.ridge from my slides and only teaching the glmnet approach. There's that bug, and I just hated to tell you to put all your eggs in the basket of buggy code, even if there's a workaround that I figured out. So, for the purpose of the homework, you can do it either way you want. I don't really care. It may be slightly easier to use glmnet, but if you don't want to deal with my bug workaround, lm.ridge is fine too. The stuff to remember for today is that penalized regression can produce more accurate predictions than ordinary least squares in the presence of multicollinearity. To me, this is a far better approach than stepwise regression. When you fit your model, particularly if your data set's large, you may want to withhold part of your data set as a test set to make sure that you're not overfitting your data. And if you want to choose lambda for your penalized regression models, you can use cross-validation. And our commands for today, lm.ridge, select, and then matrix multiplication, glmnet. The details are on the previous slides, and we're out of time, so I won't belabor the point. Any questions about anything today? Okay, next week we'll go to ANOVA, which should be significantly easier to understand than some of this stuff. I know it's a little hairy, but I think it's important. Then quite honestly, after that, most of the rest of the class will just be random topics that people in the class have told me if they're interested in. There won't be any homeworks about the rest of the material after ANOVA, and if it appears on the final, it won't appear in great detail. So hopefully people still keep coming to class, but just as an FYI, if there's stuff that you want to learn in this class that you don't know if we're going to learn, feel free to shoot me an email, and I'll try to prepare a lecture on it if I don't have one already.